So 1 by 1 unit area, how much charge is present over there, so that I can multiply it with the total area and get the total charge on the surface. That is what sigma is. Okay. Now coming back, so we have the potential. This is how much the potential is. Therefore, I can now get the capacitance C. Capacitance C is equals to Q upon V, which gives me epsilon naught into Q upon sigma into D. Okay. Now sigma, as we are saying this, sigma is essentially what? Total charge upon total area. This is what sigma is. So I can put the value of sigma over here, the Q cancels out, and I am left with epsilon naught into A upon D. This is my capacitance for a parallel plate capacitor with no dielectric. Okay, very straightforward once you understand the concepts of it all. Now, what happens when we add a dielectric? This is the tricky thing, but not so tricky as well. Quite easy actually. Okay. What happens when I add a dielectric? Let's clean this diagram a little bit so that you understand better. Whoops, I just literally cleared out the entire diagram. I could have made it from the beginning, but okay. I'm putting the charge on the plate on this side this time, so that the internal charge is clear. This is minus Q. Now, due to, as I put the dielectric, imagine the dielectric with a boundary like this. Okay, it's almost touching the plate, but I'm separating it so that it's clear for you to understand. Now in the dielectric, the electric field due to the capacitor is creating a dipole moment inside. Now the dipole moment is essentially what is pulling the electrons and the protons inside the molecules in separate ways. So what is happening? The positive side is this way and the negative side is this way. Okay, there's a separate video on this. Please do go and watch it. The effect of dielectric, effect of an external field on a dielectric. So I'm not going to cover all of that here, but what is happening in a dielectric is, because of the field of the capacitor, the molecules get induced with the dipole. The dipoles align, and what happens is, at the surfaces of the dielectric, which is on both the sides, at the surfaces of the dielectric, charges accumulate. Positive charge towards the direction of the electric field and negative charge opposing to the direction of electric field, creating a pseudo electric field inside the dielectric, creating a pseudo electric field inside the dielectric. Let's say the charge over here, or the surface charge over here, is sigma p. Obviously this will be positive, and here it's sigma p negative. Why sigma p? Because it is different from the surface charge density of the plates, the capacitor plates. Okay, so now on the capacitor plates, total charge is actually now equal to sigma, which was the original surface charge density, minus sigma p, because on both the sides sigma p is cancelling out or neutralizing it to a certain extent, right? Makes sense. But as I do this, I also realize that this sigma p is a result of the electric field by the capacitor itself. As a result of the electric field by the capacitor itself. So, electric field is directly proportional to sigma p, which implies sigma is directly proportional to sigma p. Okay, why is that again? Because electric field is equals to sigma upon epsilon naught. Epsilon naught is a constant in any way, so sigma is directly proportional to sigma p. At the same time, sigma is also directly proportional to sigma minus sigma p, right? I can totally do that because the difference, if I'm getting this, then the difference is also directly proportional to this. And so I can get a new relation over here, which is sigma upon capital K. Capital K is the proportionality constant once I remove the proportionality sign to give me this relation. Now, why did I take the proportionality sign below? That is, why did I take it in the denominator? Is because sigma minus sigma p will be less than sigma itself. That means it should be in decimals. That means to take a positive whole integer, if k is greater than 1, then this amount will be less than 1. Okay. So, important criteria that k is greater than 1. Important criteria that k is greater than 1. Okay. So, once we have this, now we can simply get the effect of dielectric in our case. So, the effect of dielectric would be finally E will be equals to, okay, so once we have that, sigma upon k minus sigma p, so I can write wherever sigma minus sigma p comes in, I can write sigma upon k. So when I am trying to find the electric field, the total electric field now is essentially sigma minus sigma p into area into epsilon naught, right? Oh, did I write something wrong? Sigma upon, sorry, this will just be this, okay, because that was the electric field over here. So I can write this as sigma upon k into epsilon naught. Okay, sigma upon k into epsilon naught. Now the V will be this into D, right? And therefore my capacitance will be equals to Q upon V, which is equals to Q is Q upon sigma D into k into epsilon naught. Now Q is what? Q is essentially, so this will also be QP. This will also be QP because that is the total charge on the plates now. Sorry. This will be Q minus QP. Q minus QP, right? Because that is the total charge on the plates now. So once I have Q minus QP, how much would that be? This is essentially sigma is equals to Q upon A. So the A remains the same. So I will have Q minus QP will be equals to sigma minus sigma P on both the sides into A. So I will multiply this with sigma minus sigma P into A to K epsilon naught upon sigma d would be finally E will be equals to sigma minus sigma P upon epsilon naught. This will be the electric field inside the capacitor now. This implies that V, which is the potential, will be equals to sigma minus sigma P upon epsilon naught into D, right? And but this also transforms into, since we got sigma minus sigma P equals to sigma upon K, I can replace sigma minus sigma P with sigma upon K into D upon epsilon naught. Important, very important. Simplifying it further, sigma can be written as Q upon A to K epsilon naught into D, right? Now I get the capacitance, and how much is the capacitance? Q upon V, which gives me Q and Q gets cancelled out, so I'm left with A into K into epsilon naught upon D, and this is my new capacitance after I've put in the dielectric. Obviously K is greater than 1. Okay, so epsilon, I can replace K into epsilon naught. K into epsilon naught can be written as epsilon, which is called the permittivity of the substance of the material that we are working with, and it's an important understanding. Okay, so epsilon upon epsilon naught was the permittivity of vacuum, so epsilon upon epsilon naught gives me K, which is again a very important number. Okay, K is essentially the dielectric strength, constant of dielectric strength, or just dielectric strength. Okay, so that is what the difference is between them. So you can see that the capacitance of a capacitor when I put in a dielectric increases by a factor of K, and K is the constant of dielectric strength, which tells us how much of charge that the object can hold. Okay, so that is it for this video. If you liked it, do subscribe and share the video with your friends and colleagues and whoever, and put down your comments in the box below, in the chat box below, so that I know which videos to take up next and which problems you have in the subject of physics and chemistry both. Okay, I'll see you in the next video.